In this video, we're going to have a look at 4 examples which involve an expression to a power. In fact, the last 2 examples will involve a product which still includes a bracket to a power. Of the first 2 examples, we'll notice that the first one is a linear expression, and the second one, whilst it doesn't have to be quadratic, involves a higher power than just x to the 1. Let's have a look at the first example. In this case, we've got the integral of 5x plus 2 all cubed. The safest way to integrate any expression to a power is to expand the brackets, or in other words, multiply out 5x plus 2 by itself 3 times. It might be wise to pause the video here, expand the brackets and simplify, and see if you agree with the expression we come up with. So now we antidifferentiate the expression 125x cubed plus 120x squared plus 60x plus 8. We can go through this term by term. So the first term will raise the power of the x from 3 to 4 and divide by that new power, plus 120x cubed divided by the new power 3, 60x squared divided by the new power 2, plus 8x, and then plus a constant. All of that can be simplified to what's shown here, and the 125 over 4, because it's a simplified fraction, can be left as is, or it can be written as a decimal, as shown here in the last line of working. Still on the same theme as example 1, let's have a look at another linear expression raised to a power. In this case, 7x minus 3 to the power 5. Now expanding this bracket will take considerable time because of the power 5. So we need to come up with some other approach. To do this, let's first of all examine the differentiation of this expression. To apply differentiation here, we need to consider the chain rule. So we'll consider the inside of the bracket 7x minus 3 to be an individual term for the moment. We take the power 5 and we place it at the front of the bracket, and we reduce the power by 1, so it becomes 4. We then consider the inside of the bracket and multiply what we had before by the derivative of 7x minus 3. In other words, multiply this expression by 7. Now let's consider what process we need to adopt to reverse this differentiation process. In other words, to anti-differentiate or to integrate. What we need to do is remove the value 5, which is at the front of the brackets. We can do this by dividing the first part of our differentiated expression by 5. We also need to increase the power of the bracket by 1, and we do that just by adding 1. And the last thing we'll do is consider the derivative of the inside the bracket, which is 7, and we'll divide by that value to remove it. So we get back to our original expression, 7x minus 3 to the power 5. Now we need to be careful of the derivative of the inside of the bracket. Whereas the 5 and the 4 are just constants, the 7 is the derivative of the inside of the bracket, and that may be an algebraic expression. Let's refer back to our original expression 7x minus 3 to the power 5 and its derivative. To reverse the process, we can see that our derivative has a bracket to a power. So we know that that's a core part of our solution for the antiderivative. The 7, which is in brown, represents the derivative of the inside of the bracket. That also is a crucial piece, keeping in mind it might be an algebraic expression, whereas the 5 is just a constant. We can manipulate that to allow us to do the antiderivative process. Let's have a look at a possible rule and how we could apply that to further examples. Let's first of all label our bracketed expression as our function, in other words, f at x. What happens is that the inside of our integral must have that function to a power, in this case n, and it must be multiplied by the derivative of what's inside the bracket. You'll notice at this stage we've left off the 5. That's because our solution for the antiderivative will become f at x to the power n plus 1, all divided by n plus 1. That's where the 5 basically gets taken into account from our example, and then plus a constant at the end. Let's have a look at applying that to a few more examples. In this example, we could expand our bracket 5x plus 2 cubed and resolve the integral by looking at each term. That's fine, but it can take some time. So let's have a look at our new rule. We're saying we have a bracket to a power. Ideally, what we want to do is make sure that's multiplied by the derivative of the inside of the bracket. So whilst we have 5x plus 2 all cubed, which matches the green in our rule, we don't have its derivative. So the next step will be to see if we can actually place the derivative of the inside of the bracket inside our integral. We know the derivative of 5x plus 2 is 5. It's just a constant. So we can multiply our original expression 5x plus 2 all to the power 3 by 5, and we can see that in brown. What we've had to do as well though, and we've got this in purple, is multiply the expression in the integral by 1/5. That makes sure that we keep equality with the original integral of 5x plus 2 all to the power 3. Let's have a look at now how we apply the rule. We can see here at the base of the picture that the bracketed expression now increases its power by 1 to n plus 1 and is divided by that new power, n plus 1, and there is a plus a constant at the end. So let's see how it applies to our example, which is 5x plus 2 all to the power 3. The 1/5 at the front of the integral remains, that's not touched, it's just a constant. And the bracket inside is increased by a power of 1, in this case it becomes 4, and divided by that new power. This can be tidied further by multiplying the denominators. So 5 multiplied by 4 is 20, and the top line of the fraction is 5x plus 2 all to the power 4. Of course, this has a constant added at the end as well. Let's have a look at another example where the inside of the bracket is not a linear expression, in this case 3x squared plus 1. So judging by what we did previously, we're looking for its derivative, which we can see here in brown, so we can justify this rule. Now the derivative of 3x squared plus 1 is 6x, and unfortunately we can't introduce that inside the integral because it involves a variable x. If it was a constant, that would be okay. So in this case, we can't apply this rule for the bracketed expression. The only option we have is to multiply it out and simplify. We can see here that by doing that we get the expression 9x to the 4 plus 6x squared plus 1. So to anti-differentiate this, what we're going to do is look at each term individually, raise the power by 1, and divide by that new power. And at the end of that we'll add a constant. If we do that, we end up with 9/5 x to the 5 plus 2x cubed plus x plus c. This is as simplified as it will get, but what we can also do is change the fraction at the front 9/5 so that the coefficient of x to the 5 becomes 1.8. Let's have a look at another option, this time where we have a product of algebraic expressions. In this example we have one bracket to a power 6 and the other bracket 4x plus 2 just to the power 1, or basically it's by itself. According to our rule, if we have one bracket to a power, in this case we'll say to the power n, ideally we want it multiplied by the derivative. We've got it here shown in brown, f dash at x. If that's the case, then we can write our solution down automatically. F at x to the higher power, in this case n plus 1, divided by n plus 1 plus a constant. So we'll look at the bracketed expression which is to the power 6 in isolation, and we'll call this f at x. So if f at x is equal to x squared plus x, we then need to identify its derivative. And in this case the derivative is 2x plus 1. We now need to look at how this associates to the other bracket, in this case 4x plus 2. And we can see that we can write 4x plus 2 as 2 outside of 2x plus 1. In other words, if we factorize 4x plus 2, we do identify the derivative of the other bracket. So now the next step is to write our integral in a form where we can apply the rule. We can see in green we've got f at x, which in this case is x squared plus x, and we've raised that to the power 6, and we've got its derivative in brown, 2x plus 1. And of course we've factored out the 2 at the front of the integral so we can isolate it to use our rule. So using our rule, we can see the solution is x squared plus x to the higher power. In this case it would be 7, all divided by 7, plus a constant. And of course this expression at the start, x squared plus x to the power 7, is multiplied by 2 because we factored that out of the original integral. Now let's consider our next example where we've got two brackets. In this case we've got 5x squared minus 4x raised to the power 3. We'll call that bracket f at x because we'll try and identify to see if 5x minus 2 matches the derivative of what's inside that bracket. So we can see by our rule that we're trying to find the derivative of f at x, so we can apply the rule where we raise the bracket to a higher power and divide by that new power. So let's call f at x equal to 5x squared minus 4x. We'll identify its derivative, which will be 10x minus 4. Now we look to see if there's a connection between 10x minus 4, the derivative, and what's in the integral, which is 5x minus 2, and we should be able to identify that 10x minus 4 is twice 5x minus 2. Alternatively, we can write 5x minus 2 as 1/2 of 10x minus 4. We'll include that in the integral, and now what we can do is apply our rule. We can see in green that we've got f at x, 5x squared minus 4x, and that's raised to the power 3. And we've got the derivative of the expression in the bracket, in other words 10x minus 4. So our solution will become 5x squared minus 4x raised to the power 4 divided by 4. And that's all multiplied by the factor of a half, which we took outside the integral. We can now simplify our solution by multiplying the fractions together. 1 multiplied by the bracket, of course, will still leave us with 5x squared minus 4x to the power 4, and the denominators will become 8. We still have the plus c at the end of our solution, so the final integral becomes 5x squared minus 4x to the power 4, all divided by 8, plus c.